So hey everyone, we are Group 2 and myself Harish Rajve, and we have Abhishek, Ilakya and Vidyadhar. And our topic for this project is basically to understand the mechanics of fractures and failure modes in graphene. So to start off, we'll say what is graphene. So graphene is basically a single layer of carbon atoms. So from the material we are well aware, which is graphite. So in other words, it's basically a two-dimensional material because it's just a single layer and we don't have a third dimension. And we can see it has a honeycomb structure and it has exceptional properties such as higher heat and thermal conductivity higher than copper and a lot of strength. It's insanely durable and higher. It has high strength, and we have a wide range of applications of graphene because of its uh, properties which we have mentioned above. But right now, the graphenes are pretty much used in electronics and other energy storage devices. And we have so taken a lot of research papers to understand this mechanics even more precisely. So one of this research through this paper we can this paper basically goes through all the mechanics and other parts of graphene. So basically graphene under tensile stress it experiences a comparatively large deformation compared to the other materials, and it has two deformation modes, basically PW1 and PW2. That's based on the bond angles and the lengths, as we have seen in class how much the bonds and the atomic structure influences the deformation. And graphene exhibits an negative Poisson ratio compared to the non-regular Poisson ratio, where if we elongate the graphene tensile, the lateral dimension decreases. And this paper also covers other test experiments and other effects such as buckling, etc.
I am Vidyadhar. This paper is about the fracture strength and fracture toughness of graphene using MD simulations. The objective here was to address the validity of Griffith's theory and AW ratios used for predicting the graphene's fracture properties. In terms of methodology, the team performed molecular dynamic simulations on a hexagonal lattice structure of a monolayer graphene sheet. With respect to research findings, the influence of the AW ratio, the team systematically investigated the influence of this ratio on the fracture toughness of the graphene, where A represents crack length and W represents the width of the graphene sheet. The team defined the lower bound of AW ratio beyond which the Young's modulus starts to decrease with increase in crack length. As you can see in the graph, beyond certain value, the Young's modulus starts to decrease with increase in crack length. In terms of fracture toughness initially increases with the increase in AW ratio, reaches a peak value, and beyond which it starts to decrease with crack length. Finally, with their results, the team has recommended the AW ratio to be in the range of 0.15 to 0.45 to have better predictions on the graphene's fracture toughness.
Uh, Hi, this is Ilakya. I'll be doing a literature review of fatigue of graphene. The objective of this paper is to investigate the fatigue behavior and damage mechanism of 2D materials such as graphene and graphene oxide. So the experiment testing and simulations were done to evaluate the long-term reliability and potential application. The image over here shows the fatigue testing of 2D materials, and the methodology involves preparing monolayer and few layer graphene oxide films, conducting fatigue testing using AFM setup, and monitoring amplitude and force signals. Experimental testing captures fatigue behavior while simulation provides the insights into it. The study combines experimental and computational approaches to understanding fatigue mechanism in 2D materials like graphene and graphene oxide. So, in conclusion, the research findings are the simulations which highlight the molecular dynamics in graphene and progressive damage in graphene oxides to provide the insights into fatigue behavior in 2D materials. Abhishek will be taking over.
Hi, this is Abhishek, and this paper is about the in situ fracture toughness measurement of multi-layer graphene. The objective of this research is to measure the fracture toughness of different numbers of layers of multi-layer graphene using their own custom designed MEMS tensile tester, which is shown in figure 3. And they also visualize the test under SEM imaging, which is shown in figure 4. And the methodology they use is chemical vapor deposition process to grow different numbers of layers of graphene over each layer on copper foil. And they also pattern the graphene to fit the area of the MEM stage so that unnecessary graphene is not covering the MEM stage, which would hinder the SEM imaging. The step-by-step process is shown in figure 2. Coming to the research findings, the numbers of layers of graphene they use for this study are 5, 7, and 12. And after doing the tensile testing, the fracture toughness of different layers of graphene were found to be 22, 71.3, and 145 joules per meter square, respectively. This highlights that the toughness increases with the numbers of layers of graphene. So here are the references we used to conduct this project, and there are different papers we are going to review further. Yeah, thank you.